resources, and we invited Professor Hehl to come and give a series of lectures, and Professor Hehl very graciously and kindly agreed to come. And Professor Hehl has published a recent book called The Gauge Theories of Gravitation. I think he has done a service to the community by looking over all the relevant and important literature and put together what he thinks is the very pertinent literature. And also it comes with very insightful commentaries, including some criticisms to the people, which I'm sure Professor Hehl will go into. Now, actually, I'm not the most qualified person to introduce Professor Hehl, because there are people here that know Professor Hehl much longer than I have, Professor Newell, for instance. But just for information, Professor Hehl is an expert on many topics in gravitation. He is considered an authority on what matters of torsion in the world. Okay, so let's welcome Professor Hehl for his first two lectures.
I'm really overwhelmed by this really very kind introduction, and I'm grateful to Professor Tsing and so for inviting me, and I'm grateful for the National Center of Theoretical Sciences, Focus Group Gravitation and Focus Group Cosmology and Astrophysics for having this chance to present to you what, gauge theory of gravitation. You could use it in singular, or you could use it in, I think, as such, it should be called gauge theory, perhaps in singular, of gravitation. Because it's a certain framework which has developed over the last 50 years, perhaps, and which makes very clear statements what gauge theory of gravitation should look like, how gauge theory of gravitation should look like. I've collaborated with Blagojević from Belgrade. Blagojević is the core of from Belgrade. And a lot of work jointly with Yuri Obukov from Moscow. So this book is written with Milutin Blagojević, but also there are pieces which overlap heavily with what I did jointly with Yuri Obukov and other people. The part, and roughly, my plan is to teach about half of this book. I mean, the book is a lot of reprints of what I consider to be, or what we consider to be the classical papers of gauge theory. There may be different opinions whether this selection was good or not so good, or whether we missed some other people which one should rather have put into that book. But this is always the case if you have to review a subject, that you have to make a critical analysis. So the part A of the book is really, it's a quasi-historical piece, the rise of gauge theory of gravitation, gauge theory of gravitation up to 1961. Up to 1961. Now, you may wonder whether this 1961 has a secret meaning. It has a meaning, but this is not secret. At this time, there were papers by Sciama-Kibble, which established the framework for gravitational gauge theories once and forever, I think. And this is a sort of a watershed between the development, where a lot of geometry and physics was brought in, and finally a breakthrough 1961. And I want to recount this rise of gauge theories of gravitation up to 61 in a short version. So in chapter 1, I should say that, of course, you can always ask questions in between. I was asked by somebody whether I would distribute exercises or something. Now, Professor Geng told me most students have so many duties that they would hardly available for making exercises. But if some of you want some exercises, then you can just signal to me, and I will write some problems which you can solve, reading problems or simple computations. It is very important, and if I look at some new papers also on gauge theories of gravity, that people are sometimes not very familiar with formalism. So there is on the one hand side in Einstein's theory tensor calculus, in the gauge theories is also exterior calculus. At least one of the formalisms you should have command of or should learn and this is partly underdeveloped because the formalism is an important tool for bringing our thoughts into a correct, coherent framework. So chapter 1, from special to general relativity. As I said, it's quasi-historical. Special to general relativity, quasi-historical general relativity, because usually I can only drop some names, and this is of course not what a historian would do. And I don't mention a lot of names, which perhaps should also be mentioned. But I want to give you always a certain temporal framework. Special relativity was developed 1905, mainly by Lorentz, Poincaré, and Einstein. And general relativity was developed 1950, mainly by Einstein, but is an important contribution by Hehl. And so this is from special relativity. As you know, of course, this is what is that one had a problem. When Maxwell's theory was discovered, Maxwell's equations were formulated in 1863. Maxwell's equations were formulated in 1863. And these are not the equations which are on your institute on the outside. They are already a simplified version for elementary particle physicists, you know. I'm sorry to say that. And then one had, of course, the electromagnetic field. It was Maxwell's theory was proven to be correct because they predicted electromagnetic waves. I mean, first of all, Maxwell could include light as electromagnetic wave, that he found out himself. And then, of course, he predicted the whole spectrum of electromagnetic waves. And Heinrich Hertz, 1886, then discovered the electromagnetic waves. And this made Maxwell's theory basically, well, since that time it was universally accepted. Maxwell had big difficulties convincing his contemporaries of his theory. And the experimental breakthrough made it all. And then, of course, we had classical mechanics. And classical mechanics, well, one often says non-relativist Newtonian mechanics, which also has a Newtonian mechanics, which, well, is just in order to give it out. 1687 is when Newton published his Principia. There was a clash. If one introduced massive bodies in Maxwell's theory and looked in the motion of these bodies and prescribed the laws of classical mechanics, then this was a disaster. It didn't lead to a correct theory. So that explains the title of Einstein's paper of 1905 on the electrodynamics of moving bodies. The vacuum field of Maxwell's theory was okay and proven by the experiments of Hertz and others. But the motion, as soon as you put these bodies, I mean, the Hertz was taking place basically when the wave was already absorbed from the source and in vacuum, and this proved Maxwell's vacuum equations. But the material bodies which moved and which were charged or uncharged, this was a problem which could not be solved with classical mechanics. So Einstein formulated two principles: the special relativity principle, the equivalence of all inertial frames for mechanics and all effects in nature. And the second principle was his principle of the constancy of light. And these two principles then led to special relativity. Okay, and special relativity was formulated in 1905, but then Minkowski, in a paper 1908, incidentally he was one of the teachers of Einstein and always thought that Einstein was not very bright. And when Minkowski published this paper, he said something like, Einstein said something like, now our good physics has fallen in the hand of mathematicians, and nobody understands it anymore. You know, but later, 2 or 3 years later, he revoked this statement because he discovered that only by using the methods of Minkowski, he could formulate gravitational theory successfully. So the 4-dimensional version, I'm sorry to say, if I talk about 4 dimensions here, you know, the 4-dimensional version was decisive for building up general relativity, which of course also Chopin knows very well, but I mean, if you bring in quantum field theoretical conceptions, then the picture may change. I mean, that is what we have heard in this conference in last weekend. So Minkowski formulated geometrical space-time, the Minkowski space-time. So in section, what is it called? 1.1. 1.1 is called Minkowski, just Minkowski space. Minkowski space. There are hooks in libraries which are called Minkowski space, and they start with a sentence like Minkowski space is the space of special relativity and it's a vector space. And already that statement is wrong, because Minkowski space is not a vector space. Because each vector space has a preferred point, the origin. And of course the idea of a Minkowski space is it's a flat Euclidean four-dimensional space with a pseudo-Euclidean metric. So it's not a vector space, it's rather an affine space. Minkowski space M is a flat affine space. Flat affine space. So you have a Minkowski space, you have a lot of events. E, the set of all events. One event may be called P and the other may be called Q. P and Q, etc. And in such a, and we can conceive a vector space which is attached to each event. This is then the vector space, but this is sort of here a vector space, here a vector space, here a vector space. But these vector spaces are connected, or these events are connected by a translation. And this is a decisive notion. Often when people talk about gauge theories of gravity, they say, well, it must be the Lorentz group because that's a group of relativity. But this is not true, of course. A group of relativity is an inhomogeneous Lorentz group, the Poincaré group. And if we had no translations, we had no energy momentum. And Lorentz transformations relate to angular momentum and not to energy momentum. So obviously translations and rotations belong together. They are called Euclidean motions. So you have, if you make an axiomatics of such an affine space, then you have to be sure that you fulfill certain axioms which I'm not going to spell out in great detail. So you have, for instance, the event P, O plus, this is not an ordinary plus, V, which is a vector, which I call V. This vector space has vectors, small v, small w, etc. Plus a vector is equal to Q. Please be careful, this is an event, and this is an event. But this is a vector defined in this vector space. So this is a fundamental structure, and now you have to formulate, and you have, of course, for each event you have coordinates, an event. You have coordinates x0, time coordinate x1, x2, and x3, or for short, x I, where I transform 0. And this translation is what mathematicians call a free transitive operation. The transitive operation, I would like to refer to the book of Snapper. Snapper and Troyer. And it's simply called metric affine geometry. Metric affine geometry. I will have the number 1971. In New York, 1971. 1971. And what we want for our affine space is first that we have it's so-called simply transitive. If we have a, let me make a sketch. If we have an event P, and if we have two vectors, two translations, here a translation V, and here a translation W, and then we can, on the one hand side, take the event and execute a translation, which is just the vector, the sum of the two vectors, which is of course in a vector space well defined, and then we come here to an event R. So P O plus, and this is now a vector plus, this is an ordinary plus in vector calculus plus W, and this gives us the event R, but on the other hand side, we should be able first to execute the B. We have here our event P and go here with the translation to this point, and then we take a second translation W, which is not very parallel, and we come to the same point. So that must be that P plus O plus V, O plus W results in the same. We have to establish this as an axiom such that this takes the case, because that's what happens in a Euclidean space. And the second main axiom which one has to do is that the vector between two events is uniquely defined. So that if you have if you have the event Q, then you can reach it from the event P by a unique vector, namely just the difference between Q and P. Translation Q minus P. And these properties you have to program into your axiomatics. So this is to show that in an affine space, translation is a fundamental concept. Translation is a fundamental concept, often forgotten in the literature. I saw recently a book by Blagojević shortly before he died. He's a very famous quantum field theoretician. Most of the stuff he writes I don't even understand. He wrote his last book on the meaning of translation in quantum field theory. I mean, so for somebody who would like to see that from a more elevated point of view, the meaning of translations, return to this. So far we have then an event space of events. We have a translation, and we have a vector space. But this is not yet a Minkowski space. A Minkowski space, additionally, requires a metric. Requires, well, a tool for measuring angles and distances. And that's a metric, and since we have, what I forgot to say, our coordinates are in rectilinear coordinate systems. So these coordinates which I denoted here are with respect to a rectilinear coordinate system. In affine space, there's so far no orthogonality, which only comes in through the metric, so it's rectilinear coordinate systems. We need a metric, and this, and we need a pseudo-Euclidean metric. Or with pseudo, no, I shouldn't say pseudo-Euclidean metric. We need what the mathematicians nowadays call a Lorentz metric, even though it was invented by Minkowski. We need a Lorentz metric, which has a pseudo-Euclidean signature, that is plus, minus, 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 or the other way around. Okay, so if you have a metric and you feed into vectors, G parenthesis V, comma W parenthesis, we find Gij times Vi times Wj, summation implied, of course. And if you write it in longhand, it's because it's a V0, W0 minus VA. So that is our metric.